we continue the lecture on NP-completeness. Let's recall how we proved that a problem is NP-complete. First of all, we proved that the problem is in NP, and for this we can use the certificate-based definition of NP. And then we proved that the problem is NP-hard. To show that the problem is NP-hard, we need to reduce from a known NP-hard problem. So we select some known NP-hard problem and then give a reduction to our problem. The reduction, of course, needs to run in polynomial time, and it needs to produce an equivalent instance. Okay, so we already know that CNF set is NP-complete, and we saw that we can restrict the length of the clauses to get the K-CNF set problem. So here we want to show that 3-CNF set is NP-complete. Okay, so first of all, we need to show that the problem is in NP. But 3-CNF set is a special case of CNF set. That's why we can't just run any algorithm for CNF set. This also works for 3-CNF set. And since CNF set is in NP, so it has an algorithm, or it can be solved by a non-deterministic Turing machine in polynomial time. Therefore, 3-CNF set can be solved by one as well. Okay, so now this establishes membership in NP. Alternatively, we could have used the certificate-based definition of NP, and then we could just have said that assignments to the variables are certificates because, well, a certificate that actually satisfies the formula, such a certificate, can be has polynomial length, and it can be checked in polynomial time whether actually it is a valid certificate for this instance. Okay, so the second step is to prove that the problem is NP-hard. And for this, we reduce from a known NP-hard problem. We know that CNF set is NP-hard. So let's reduce from CNF set. So if we reduce from CNF set to 3-CNF set, and we are given some CNF instance, so some formula in conjunctive normal form, it might have long clauses. So we need to find a way to shorten these clauses so that all the clauses have at most 3 literals. But of course we can't lose any information because we need to produce an equivalent instance. So given one clause that has more than 3 literals, we want to replace it with probably several clauses that all have length at most 3. So for the clauses that we are given in the input that have length at most 3, we can just copy them. And for the longer clauses, we have to do something, replace them by something that's equivalent. Okay, so if F is our CNF formula, now the reduction algorithm does this transformation. So it constructs a 3-CNF formula F prime as follows. So for each clause, it does something. If the clause C has at most 3 literals, then we just copy it into the resulting formula. Otherwise, so let's say we denote the literals of the clause by L1, L2 up to Lk. So k is at least 4. Now we can do the following. So we'll replace this clause by a bunch of new clauses. And for this, we actually create k minus 3 new variables that we use to link the new clauses. Okay, so how do we link a clause? So these are the clauses that we are creating here, down at the bottom. And okay, so the first clause contains L1, L2, and also Y1. So y1 is one of these new variables that we added to link the clauses together. And basically, what y1 does, it tells us, so let's see. So if y1 gets the value 0, then either L1 or L2 must get the value 1, because we need to satisfy this clause. So if y1 equals 0, then L1 or L2 satisfy the clause, and therefore also the clause C is satisfied by the same assignment if we just project it onto the literals that were in C. Okay, so if y1 is 0, then we satisfy the first clause. But then, since y1 is 0, the second clause is automatically satisfied, because then not y1 is equal to 1. And that's why, since not y1 already satisfies the second clause, now we can set y2 to 0, and that's why not y2 is 1. So the third clause is satisfied. And because the third clause is already satisfied by not y2, we can now set y3 to 0, and then this will propagate, and then here not yk minus 3 will be true as well, and we don't need to set lk minus 1 or lk to true. Okay, so basically, because L1 or L2 satisfied the first clause, we had the advantage that we could set y1 to 0, and this then enabled us to propagate and satisfy all the remaining clauses by the y variables. If, on the other hand, neither L1 nor L2 satisfy the first clause, then we have to satisfy the first clause by setting y1 to 1. And that's why not y1 is 0. And then we either need to satisfy the second clause by L3 or by y2. So if we satisfy it by L3, again we can use the y variables to propagate and make everything else true. If L3 is false, then we have to set y2 to true, and that's why not y2 is false. And so we go to the next clause and next clause, and at some point we need to set one of these L variables to true. And the way we set it up here makes it exactly so that one of the L variables needs to be true, and the y variables are used to propagate this information. Okay, so and this worked because we are able to use clauses of length 3. So why can't we use the same reduction for 2CNF? Well, it's because we need, you see, we need 2 y clauses for the middle clauses here. And we want to add at least one of the original literals that we had in the clause C. And that's why we need at least 3 literals to be able to transform C into an equivalent set of clauses. Okay, so now we just need to show that f is satisfiable if and only if f prime is satisfiable. So the way we do this is that we show that, well, if f is satisfiable, then f has a satisfying assignment, of course. We need to show that if f has a satisfying assignment, then f prime has a satisfying assignment. And for this we can just use the same assignment. We just now need to set the assignment to the y variables in the appropriate way. But this is an if and only if, this statement, and so we also need to show the reverse direction. So if f prime is satisfiable, we need to show that f is then also satisfiable. Alternatively, we could show that for the second direction, that if f is not satisfiable, then f prime is also not satisfiable. Okay, and we also need to show that f prime can be computed in polynomial time. but this is quite easy to do in pseudocode. So we can, because we're just copying short clauses into f prime, and we are doing a simple transformation for the long clauses. What we need to note here is that the resulting formula doesn't have exponential size, so it still only has a polynomial size. Okay, so we showed membership in NP, and we showed that the problem is NP hard, so therefore 3CNF set is NP complete. A few details here are missing, namely we would need to formally show that if f is satisfiable, then f prime is satisfiable, and if f prime is satisfiable, then f is satisfiable. Okay, our next problem is the clique problem. So a clique in a graph is a subset of vertices that are all pairwise adjacent. So in this example graph here, like the red vertices, they form a clique of size 3 because, well, they're all pairwise adjacent. So the input to the clique problem is a graph G and an integer k. And the question is whether G has a clique of size k. We want to show that clique is NP complete now. So let's think about membership in NP. So what's a certificate? So a certificate is just a set of vertices, and there's a verifier that checks whether this set of vertices is a clique of size k. So whether it has size k, and whether for every 2 vertices in this certificate, in the set of vertices, we have an edge in the graph. So a certificate would be a set of vertices, and the certificate would be valid if it actually forms a clique of size k in this graph. Okay, so that shows that clique is in NP. And now to show that clique is NP hard, we'll reduce from 3CNF set. Okay, so we have a formula like the one on the bottom here. That's a 3CNF set formula, and now we want to obtain an instance for clique and construct an instance for clique in polynomial time. So remember always to reduce from a known NP hard problem to the problem that we want to show is NP hard. So we have k clauses in our formula, and now we want to construct a graph that has a clique of size k if and only if f is satisfiable. So the number of clauses in the formula will be equal to the size of the clique that the clique problem asks for. Okay, so what am I doing here? So now for each occurrence of literal here, I created a vertex. So for the first clause, I created these 3 vertices. For the second clause, I created these 3 vertices. And for the third clause, I created these 2 vertices. So every occurrence of a literal becomes a vertex. And I have grouped them the same as the clauses. Okay, so what am I doing now? So basically, I want to add an edge between 2 of these vertices if the assignment is compatible. Okay, so like I can simultaneously set not x to true and not y to true. So that's possible, right? I can simultaneously set y to true and x to true. But I cannot add y to true and not y to true. That's why I do not have an edge between y and not y. Okay, for each clause, I now need to find, so in the satisfiability problem, I need to be able to set at least one literal to true in each clause. And So that's the thing that a non-deterministic Turing machine would guess. It could guess for each clause which literal will satisfy this clause. And here in the clique problem, what needs to be guessed is, well, the set of vertices that form the clique of size k. And so this assignment, or this choice of a variable or a literal in the clause that satisfies the clause will correspond to the choice of one vertex in the clique. And I need to make sure that this is compatible. So if I choose y into my clique for the first clause, I cannot choose not y in my clique for the second group of vertices here that correspond to the second clause. Okay, so we add an edge between two vertices if they occur in different groups here. Like I will not add edges between not x and y because I only need to satisfy each clause once. I could satisfy it multiple times, but I only need to choose one literal that satisfies the clause. So in the same way, I will only choose one vertex into my clique from each group of literals. Okay, so we will not add edges between vertices of the same group, and we will also not add edges between vertices where one is the negation of the other one. So we'll only add edges between compatible assignments. Like setting y here in the first clause to true, like this y, and setting this y to true as well, that's compatible because it doesn't create any kind of conflict. So we do have this edge, but we don't have the edge between y and not y. Okay. So what do we get now? So now an assignment corresponds to a setting of the literals as well. So an assignment to variables corresponds to an assignment of literals. And we know that if the assignment is satisfying for the formula, then each clause contains at least one true literal. Now, choose a true literal from each clause, and these true literals will form a clique in the graph. The same way, a clique in the graph will give us a partial assignment, so an assignment to some of the literals, that is guaranteed to already satisfy each clause of the formula. So we can then easily extend this assignment to a complete assignment of all variables in a way that satisfies all the clauses. So for example here, in this example, I could have chosen that y is true and that x is true. So, if I have this clique here, consisting of this occurrence of y, this occurrence of x, and this occurrence of y, I know that if I set x and y to true, I will satisfy all my clauses, no matter how I assign z. Okay, and so from this formula, I constructed this graph, and we need to show that this can be done in polynomial time, and that this is a correct reduction. So for the correctness, we'll say that f has a satisfying assignment if and only if g has a clique of size k. And to prove the forward direction, consider any satisfying assignment for f, and now for each clause, we choose some literal that is set to true. And now we also look at the corresponding vertex in the graph, and if I do this for every clause and select the corresponding vertex in the graph, then I will get a clique of size k. And for the other direction, if I have a clique of size k in the graph, then we'll define the partial assignment that's compatible, or that results from this selection of vertices, and this selection doesn't create any conflict, so we'll never set x to true and not x to true because we didn't add an edge between those two. And now we just need to extend this assignment to a complete assignment of all the variables that satisfies the formula in an arbitrary way. Okay. So this proves that clique is NP-complete. Our next problem is the vertex cover. So a vertex cover in a graph is a subset of vertices such that every edge of the graph has an endpoint in this set. And the vertex cover problem has as input a graph G and an integer k. And the question is whether G has a vertex cover of size k. And one can show that vertex cover is NP-complete, and the proof of this statement is left as an exercise. Let's look at one more complicated example. Let's have a look at the Hamiltonian cycle problem. So the input is a graph G, and the question is whether G has a Hamiltonian cycle, and the Hamiltonian cycle is a simple cycle that visits each vertex exactly once, or alternatively a permutation of the vertex set such that every two consecutive vertices are adjacent, and also the first and the last vertex in the permutation are adjacent in the graph. Okay, so if you want to show that Hamiltonian cycle is NP-complete, let's first show that the problem is in NP. And for this, the certificate or valid certificate is just the Hamiltonian cycle of the graph. And now let us show that vertex cover can be reduced in polynomial time to Hamiltonian cycle. So we choose here an NP-complete problem, vertex cover, and we try and reduce it to our problem, Hamiltonian cycle. Okay, so what are the non-deterministic choices for vertex cover? Well, the non-deterministic choices are which vertices to put in this vertex cover. For Hamiltonian cycle, the non-deterministic choices is which edges of the graph do we need to add to this Hamiltonian cycle. So we somehow need to map a selection of vertices to a selection of edges. Okay, so as usual, take any instance for our vertex cover problem, so this instance is an arbitrary instance of the vertex cover problem, and for any instance for vertex cover that we are given, we need to construct an equivalent instance for Hamiltonian cycle. So let's say we have an instance G, K for vertex cover, and we want to construct this equivalent instance G prime for Hamiltonian cycle. Yeah, so for vertex cover, the non-deterministic choices was which vertices do we add to the vertex cover. For Hamiltonian cycle, it is which edges do we add to the Hamiltonian cycle, or more precisely, which route does the cycle take. Okay. So we will add k vertices to G prime. So those are called the selector vertices. They basically, so we have one vertex for each choice of a vertex in the vertex cover that we can add. So in G prime, these will be called the selector vertices. Now each edge of G will be represented by a gadget of G prime. And the gadget is just a part of this graph that we are constructing. So basically, for each edge, we'll construct something, and this something is a small graph, and we call this typically a gadget. And we want to make it in such a way that the set of edges that are covered by a vertex x in G corresponds to a partial cycle going through all gadgets of G prime that represent these edges. Okay, so a vertex, in our vertex cover instance, a vertex covers some edges, right? And now in G prime, we of course need to work with the Hamiltonian cycle problem, and here we will want a part of the cycle to encode these edges that are covered by the vertex in G. There's one difficulty, which is, so in the vertex cover problem, an edge can be covered either by one endpoint or by the other one, or actually by both. And so we need to make sure that we count for this, or we allow for an edge to be covered by both endpoints. Which makes the gadget a bit more tricky, but here is one that works. So we have an edge UV in the graph G, and now we want to translate this into a gadget in the graph G prime. And so on the left here, so this is our gadget. And it will be, so these gadgets will be attached to the selector vertices and also to each other. But one of these now corresponds to the edge UV. And so basically, the edge UV needs to be covered either by adding U to the vertex cover, or by adding V to the vertex cover, or by adding both. So and here, so the first situation here is when we add the wet vertices, the wet edges into our Hamiltonian cycle. This corresponds now to selecting U into the vertex cover. And we can see here that adding these wet edges will, so the cycle will go through each vertex of this small gadget, right? So this situation here will correspond to the situation where we add V to the vertex cover. So now you see that the cycle enters on the other side, and it also exits on the other side. And still we go through each vertex of this gadget. And here we have the situation where both U and V are added to the vertex cover. And now the cycle is able to enter on the left-hand side and exit also on the left-hand side. And it can enter on the right-hand side and exit on the right-hand side. And still we cover each vertex of this gadget. So this Hamiltonian cycle will go exactly once through each vertex in this gadget. If we select U into the vertex cover, if we select V in the vertex cover, and also if we select both of them into the vertex cover. So this represents one edge of the original graph, but now we also, of course, need to put this together. So let me just illustrate to you how this would look like for a concrete instance. So on top here we have the graph G. So that's this graph, and k equals, let's say it's 2. So we have a yes instance because actually adding A and D to the vertex cover gives us a valid vertex cover. Okay. So now on the bottom here we have the instance, the transformed instance, so the instance for Hamiltonian cycle. So we have the two selector vertices here because k equals 2. And now we put them together in such a way that actually going from okay, so let's look at one vertex. Let's look at the vertex A in the original graph. So it has 3 incident edges. So somehow, and when the cycle enters here at A, at AB1, at this vertex, then it will also exit on the same side. And we set it up in such a way that now, after exiting here, it will go, the cycle can go now to the second vertex, or to the second, the edge representing the second edge that's covered by this vertex A. So we have the edges AB, AD, and AC that are covered by A. So the cycle goes from this AB gadget to the AD gadget, and then when it exits here at AD6, it goes now to AC1 for the third edge that's incident here to A. And then when it exits, now it's allowed to go back to the selector vertex, so to the next selector vertex, like S2 here. So we selected A, went through this gadget, went through the AD gadget, went through the AC gadget. Now we go to S2. Now the selector gadget here selects the vertex D. And D covers two edges, and these are DB1 and AD, these two edges. And now, after exiting the AD gadget here, it's allowed to go back to any of the selector vertices, and to close the cycle it will go back to S1. Okay, so this is a non-trivial reduction. I will not expect you to come up with such complicated reductions, but it's good to see at least one more complicated one. Okay, and if you want to read more about NP-completeness, there are some very nice books. There's the chapter on NP-completeness in the Common Adalbach book, and also Gary and Johnson have published a very influential reference book, and there's more books on the topic.